Okay, so my presentation is on geothermal energy. I'm gonna try and keep it around 5 minutes. I just did a practice run and it took a little longer than that, so try and speed it up here. But geothermal energy is a pretty exciting, fairly relatively new source of energy that's come around. It's very accessible. It's basically any region in the world has access to it. It's really consistent. It's operates year round, and there's a relatively small amount of greenhouse gas emissions compared to other types of energy sources. So the formation, kind of like an overview of how we get geothermal energy. The inner core of the Earth is about as hot as the sun is, uh, and this is a byproduct of basically three things. Leftover energy from the formation of the planet about 4.5 billion years ago, frictional forces from gravity pushing dense elements towards the core of the Earth creates heat, and then also the decay of radioactive isotopes in the mantle also produces heat. So these three things produce a lot of heat, and then through convection, the heat is brought towards the surface of the Earth, which can then be used for electricity generation with three different types of generators, which I will talk about. And then also, it can be used to heat and cool houses or buildings with a geothermal heat pump. So, first, I'll go over the three types of generators. The first type is dry steam. So, essentially, this pulls steam from underground, from a geothermal reservoir, and the steam is used to spin a turbine, which allows a generator to produce electricity. And then the excess water and steam is injected back into the ground. And then a flash steam generator is very similar, except instead of pulling steam from underground, it pulls water. And then this water is put into a flash tank and evaporated into steam to create or to spin the turbine. And once again, produce the electricity. And then the last type is a binary cycle, so it pulls hot water from the ground and runs it through a heat exchanger. And then another loop that is going through this heat exchanger contains a working fluid, which is essentially a fluid that has a lower boiling point than water. So a popular one is pentane, which has a boiling point of about 36 degrees Celsius, where water has a boiling point of about 100 degrees. So this allows so this this allows this working fluid to boil, evaporate, and turn into a steam a lot easier or at a lower temperature than the water. So this type of power plant can be used in locations that don't have the shallow geothermal resources. So this kind of goes into where is geothermal energy like really easily accessible, and then where is it a little bit more difficult to utilize. So geothermal hotspots are areas of the world that have natural hydrothermal reservoirs. So a natural hydrothermal reservoir has three characteristics. It's hot, it's somewhere around 300 degrees Fahrenheit, sometimes more, contains water, and the rocks are permeable, which means they allow liquid and gases to pass through them. So areas like this are Iceland, Italy, Austria, and then also regions around the Pacific Ring of Fire. And something that all these regions have in common is they're all around plate boundaries, so very volcanically active. And then other areas that aren't in this type of region have to use something called enhanced geothermal systems to create these hydrothermal reservoirs. And so basically, the EGS system injects a well, depending on the area, anywhere from zero point 0.6 to 2.8 miles deep. And then it injects pressurized fluid, which basically creates fractures in the rocks, and this increases the area in which heat exchange can occur. So then the water starts to go through these cracks, heat exchange happens, and then the final step is to inject a production well, which will then take this water or steam out of the ground and create the electricity. So effectively, the EGS is creating I guess, like an artificial hydrothermal reservoir underground. So there's a problem with this. There are some seismic concerns. So when you inject pressurized fluid into the ground and start to fracture the rocks, um, it makes the area more susceptible to earthquake related activities. So the heat from underground can also be used to heat and cool houses and buildings. So using a geothermal pump, and then also knowing that about 10 feet below the frost line underground remains around 54 degrees Fahrenheit year round. So this allows you to heat and cool your house depending on the season. So in the winter, there is so the geothermal heat pump is when you basically install what's called a heat exchanger underground, and it's a closed loop pipe system that contains water and antifreeze. Um, and so in the winter, you send cold water down. The cold water heats up into warm water, and then that warm water aids your heater or your heating unit in heating your house. And then in the summer, same thing. You send warm water down, it cools, comes up, and helps out your air conditioning unit. So not only does this save you money, but it also uses 75% less energy than the traditional methods. So environmental concerns, I looked at three main ones. So greenhouse gas emissions, seismicity, and subsistence. So greenhouse gas emissions, the Intergovernmental Panel on Climate Change created a life cycle emissions report. And life cycle emissions is basically a measure of the amount of emissions a power plant generates through their entire life cycle. So construction, operation, and the end of life waste management. And so as you can see, the geothermal emissions were 38, and the units are carbon dioxide per kilowatt hour of energy produced. So you have geothermal at 38, coal at 820, and gas at 490. So quite a noticeable difference there. And then also seismicity. So like I said, from the enhanced geothermal systems, injecting that pressurized water underground has created earthquakes in the past and has the potential to create earthquakes in the future. So there is a good amount of research being done on how to mitigate this. So that'd be like the main environmental concern. And then also subsistence is basically the sinking of Earth's surface. So when you're pulling water out of the ground at a rate that is greater than the rate it takes for the reservoir to replenish after you inject the remaining or the water back down after using the electricity, after using it to create electricity, then it has the potential to sink Earth's surface. So this would damage pipelines, roads, drainage systems. However, this can be managed by, like I was just saying, just limiting the amount of water that you pull out at a time and letting that underground reservoir replenish. So this is just a figure from that IPCC life cycle emissions report. So up here is coal and gas, so very high in their life cycle emissions, and then down here is geothermal, so pretty low comparatively speaking. And then also comparing it to other renewable resources like wind, hydro, and solar, kind of just in the middle. But something to note is the space required to build a geothermal plant is much smaller than wind or solar. So the space needed to produce a gigawatt hour of energy. For geothermal, it's 404 square miles, wind about 1,300, and solar about 3,200. So not only is it substantially less space needed to build the plant, but also the wind and solar are seasonal. They're seasonal types of energy sources. So like, for example, solar, you're obviously only getting it in sunny places, so that you need to be able to store it for the winter or store it for other areas of the world. And this is just going to be more expensive because you're going to have to create um, energy storage facilities, which you don't need to do with geothermal because the heat stays there year round. So the future, um, to build a geothermal plant, there's substantially more paperwork needed, like from like a political standpoint, than a like say oil plant. So that's a challenge in itself. The tax credits for oil drilling are about 30%, whereas for geothermal plants about 10%. So that's another thing. The government's not really subsidizing geothermal energy plants. Then obviously, like I mentioned earlier, mitigation strategies for seismicity and subsidence issues are needed in the future. Um, so just kind of like management strategies need to be incorporated to limit the amount of earthquakes and the surface of the earth is decaying. And then also cost. So to to build a geothermal plant, it costs about $2,500 per kilowatt hour of energy produced, whereas a gas power plant is 812, so substantially cheaper. Um, so that's just another thing that that needs to be taken into account. And then that being said, however, geological hotspots are like the Ring of Fire, Italy, Austria, Iceland. These areas are expected to grow. The geothermal energy is expected to grow in those areas by about 28% in the next 4 years. And then globally, the geothermal power market from 2018, when it was about 4.6 billion, is projected to reach about 6.8 billion by 2026. So it's expected to grow as well, maybe not as much as the geological hotspots because they don't need the EGS technology. Um, but as far as um, environmentally friendly um, sources of energy, geothermal definitely has its competitors beat. It's just a matter of the seismicity and subsistence issues, and then also getting that cost down or getting some help from governments through subsidies. And that was it. Thank you.